Bismillahirrahmanirrahim. Dear students, now we are going to discuss our chapter number 3, which is X-ray diffraction techniques, and the lecture number is 1. Single crystal X-ray diffraction, the topic which is being discussed here today. In the single crystal X-ray diffraction we use goniometer, and this is the schematic diagram showing the mechanism and process of the spectrometer or X-ray diffractometer. You can see from the left side here is the source of X-rays, which is shown by the blue lines, and in the center it is light green in color showing. This is showing the material, the sample which is being observed, and at the end it is the detector. This is instrument shown here which we use for the purpose of X-ray diffraction technique. Single crystal X-ray diffraction. What is single crystal X-ray diffraction? We are going to discuss. The introduction. An X-ray diffraction measurement. A crystal is mounted on a goniometer and gradually rotated while being bombarded with X-rays, producing a different pattern of regularly spaced spots known as reflections. It means we have a sample of crystal which is being studied. That crystal is mounted on the goniometer, and we hit the X-rays on the crystal, and when these X-rays hit the crystal, they produce the diffraction pattern there, and the regularly spaced spots are observed, which are called the reflections. The two-dimensional images taken at different rotations are converted into a three-dimensional model of the density of electrons within the crystal using the mathematical method of Fourier transforms combined with chemical data known for the sample. It means we will obtain first of all the two-dimensional images from different rotations, and when we get the two-dimensional images from different sides, then we will convert that dimensions into the three-dimensional model of the electrons density which are present in the crystal, and mathematically we transforms in that, and we can get the chemical data. If there is the poor resolution or even errors may result if the crystal are too small or not uniform enough in their internal makeup. It means we should have the sample of enough size of the crystals which can be determined or studied, and the most important, the size of the crystals should be uniform to get the regular or coherent information. If the single crystal of sufficient size cannot be obtained, various other X-ray methods can be applied to obtain less detailed information. They may be include such as the fiber diffraction, powder diffraction, or small angle X-ray scattering. It means that if we have the crystals which are not enough in size to determine by the X-ray method, then we should have to determine that very small sized crystals by different techniques, and that different techniques may be fiber diffraction, powder diffraction, or small angle X-ray scattering. And if the material under investigation is only available in the form of nanocrystalline powders or suffers from poor crystallinity, the methods of electron crystallography can be applied for determining the atomic structure. Means, on the basis of size of crystal, we can apply different techniques. If the size of the crystal is in the nanocrystalline form or nanocrystalline powders, we should have to determine the atomic structure of that crystal by using electron crystallography. For the X-ray diffraction methods, the scattering is elastic. Hence, the scattered X-rays have the same wavelength as the incoming X-rays. By contrast, inelastic X-ray scattering methods are useful in studying excitations of the sample rather than the distribution of the atoms. It means that in the inelastic X-ray scattering methods, the most important and useful phenomena for the studying excitation of sample, because we are going to discuss the atomic structure. In this technique, we are not directed, or we are not here to get the distribution of its atoms. The oldest and most precise method of X-ray crystallography is single crystal X-ray diffraction, in which a beam of X-rays strikes a single crystal, producing the scattered beams. When they land on a piece of film or the detector, these beams make a diffraction pattern of spots. The strengths and angles of these beams are recorded as the crystal is gradually rotated. Each spot is called a reflection, since it corresponds to the reflection of the X-rays from one set of evenly spaced planes within the crystal. For single crystals of sufficient purity and regularity, X-ray diffraction data can determine the mean chemical bond lengths and angles to within a few thousandths of an angstrom and to within a few tenths of a degree respectively. It means in the past, different methods of X-ray crystallography were used, and from that the single crystal X-ray diffraction is one of them. In the X-ray diffraction, we use X-ray beam to study the crystal and atomic structure. When the X-rays after scattering with the crystal land or hit the detector, and their detector the different diffraction pattern spots are obtained, which were used to study the bond lengths and bond angles of the structure. The atoms in a crystal are not static, but oscillate about their mean positions, usually by less than a few tenths of an angstrom. In the solid state, we know that the molecules or atoms are not going to move. They are only in the vibrations and oscillations, but they cannot go under the rotational or translational motions. And because they are static, they only oscillate or vibrate. The X-ray crystallography allows measuring the size of these oscillations. Why we need a single crystal X-ray diffraction? Why single crystal? Why X-ray? By the way, why is a single crystal necessary, and why are X-rays used for the X-ray crystallography? For viewing the three-dimensional structure of atoms quantitatively, it is required to satisfy the following three conditions, which are: the types of atoms are distinguishable. Second one is the position of the individual atom, which is buried inside of the molecule, can be determined even if the molecule is large like proteins. And the third condition is the view of molecules from as many different directions as possible can be obtained. In addition, the relative positions among the molecules from different view can be determined precisely. If we are going to study the crystal by single crystal X-ray diffraction, we should have the three basic conditions, which are the atom should be distinguishable. If the atoms are indistinguishable, we are not able to differentiate between atoms, and we are not going to get the exact bond lengths, bond angles for necessary for the crystal. And second one is the position of the atoms, and third one is the directions of the different molecules or atoms necessary to study. Okay, the third condition is certainly satisfied by the nature of crystals. It is the X-ray crystallography that satisfies three conditions, and currently it is the most popular analytical method to solve the three-dimensional structure of the molecule. The third condition is certainly satisfied by the nature of crystal. You can see here on the screen, this is the atomic structure. It is the regular arrangement of the atoms or particles in the crystal. You can see from the left side the green, which is large in size, showing in the center of the crystal, and other showing the particles regularly arranged. Why XRD? XRD is actually used to measure the average spacings between layers or rows of atoms and determine the orientation of a single crystal or grain. XRD is also used to study, and it is used to find the crystal structure of an unknown material, and it is also used to measure the size, shape, and internal stress of small crystalline regions. And now we are going to get the comparison between single crystal X-ray analysis and the other methods used to detect the structure analysis or structure of the crystal. In the single crystal X-ray diffraction technique, in our further lectures, we will discuss all these main points. Uh, in the start, we need for single crystal X-ray diffraction, which we have done before. And what is single crystal X-ray diffraction? This is also done before. And now in this topic we will discuss the comparison between single crystal X-ray analysis and other methods. This topic is continued, and by this topic we will also discuss the principles of X-ray diffraction. After this, we will discuss the interpretation of the data, the electron density maps, the single crystal structure refinement, the four circle or area detector diffractometer, the instrumentation of diffractometer, working of the diffractors, data processing, Siemens molecular analytical research tool SMART, Saint, the Siemens area detector integration, solving a crystal structure by single crystal diffraction techniques, use of SHELXTL and SHELX for the refinement of single crystal data, correct placement of disordered atoms during refinement, applications of the diffractometer, strengths and limitations of single crystal X-ray diffraction, advantages and disadvantages of X-rays, powder diffraction versus single crystal X-ray diffraction, Neutron diffraction, and at the end electron diffraction. This is the course content of our single crystal X-ray diffraction, and in this chapter we will discuss all these topics in detail, inshallah. The comparison between single crystal X-ray analysis and other methods. Recently, elucidation of molecular structures is becoming more common owing to the developments of various measurement techniques. Nuclear magnetic resonance, which is commonly known as NMR, mass spectrometry MS, and IR mean infrared spectroscopy are the typical examples. However, these spectroscopic techniques derive just a list of partial structures, and it is sometimes difficult to deduce the three-dimensional structure of the whole molecule. On the other hand, it is the molecular structure itself that is derived from the single crystal X-ray analysis. Single crystal analysis provides a unanimous conclusion that sometimes puts to an end to arguments over molecular or crystal structure. In a nutshell, we have NMR, mass spectrometry, and infrared spectroscopy in comparison with the X-ray diffraction techniques. By NMR, MS, and IR, we have the difficulty to deduce the three-dimensional structure of the whole molecule. By NMR, IR, and mass spectrometry, we can get only the information about the molecule, about the structure, but we cannot get three-dimensional pattern. But by using single crystal X-ray analysis, we can get the three-dimensional structure of the molecule or the crystal also. This is the comparison between single crystal X-ray diffraction, NMR, which is nuclear magnetic resonance, MS, mass spectrometry, IR, infrared spectroscopy. And at the leftmost side, these are the properties which are being comparison, which are we are going to compare the properties. First of all is non-destructive measurement. Non-destructive measurement means which one of these four techniques is non-destructive. It means this technique cannot we can say this technique is helpful for our sample. The sample once being studied is used. It is if used for an other time, so we can say it is non-destructive. If the sample is once used and it is destroyed, so that technique is known as the destructive technique. So single crystal X-ray diffraction technique is non-destructive. NMR is also non-destructive, but in the mass spectrometry, the sample once used cannot be used for the other time. We should have to take, or we should have to get an other sample for next analysis. IR is also non-destructive technique. Sample form in the XRD, we can use the crystal, and in NMR we can use liquid and solid both. In MS we can use gas, liquid, solid, and in IR we can use gas, liquid, and solid also. Measurable atomic types. In single crystal XRD we can use all type of atomic measurements. In NMR that is limited to some. In MS all the atomic type measurements are done, and in IR also. Determination of configuration, we can determine the configuration of the structure in single crystal XRD, but in NMR we indirectly determine the configuration but not directly, and by MS and IR we cannot determine the configuration. Determination of absolute structure means the exact structure. We can get exact or absolute structure by single crystal XRD, but in NMR we can determine the structure indirectly, but in MS or IR we cannot determine. Determination of crystal structure the crystal structure is only determined by the single crystal XRD, but not by an other technique, either NMR or MS or IR. As the sample preparation is concerned, in the XRD, the sample is prepared by great difficulty. In NMR, it is somewhat easy than XRD, but difficult than MS and IR. And in case of MS and IR, we can prepare sample easily. The data interpretation, we can interpret the data directly only in the single crystal XRD, but in NMR, MS and IR we get the indirect interpretation of the data. Thank you.